Let's look a little bit more at the oops, this is in the wrong slide. Let's look a little bit more at the time scales. So this is some data from long time. So this is in millions of years, 300 million years, zooming into the last 3 million years, then zooming into the last 50,000 years and last 1,000 years. So that gives you a sense of the tectonic time scales, as we call them, and orbital time scales, the glacial and millennial time scales, and historical time scales. Okay, so you can see that on long time scales you have very long time scale warming and then cooling. So we are in this last 50 million years of cooling, and global warming is happening out of that long-term cooling trend. So the question is, were we going into an ice age, and are we somehow preventing that with this global warming business? If you look at the last 3 million years, you will see that there were some 40,000 year time scales here, and then over the last 1.8 to 2 million years, it has switched to a lower 100,000 years. So these are obviously warm means deglaciation, so glaciers almost disappear. Cold means glaciation. So it's kind of a also not a very rigorous definition, because right now we have glaciers on Antarctica and Greenland and several mountains like Himalayas and Kilimanjaro and St. Helens and so on and so forth, right? Okay. So if you look at last 50,000 years, we came out of the last ice age about 18 to 12,000 years ago, and we had the abrupt warming as we expect from that asymmetry of sawtooth, and we are in this Holocene period, which is now transitioned into Anthropocene. So you can see that generally this is a stable period, and over the last 1,000 years you have a different scale as well. So here it is 10 degrees centigrade change over 300 million years, also 10 degrees over last 3 million years, down to 3 degrees in the last 50,000, and just 1 degree in the last 1,000 years. Why does it matter? Because as human beings, we mostly evolved. Modern human beings got settled as agricultural livelihood into industrial revolution during this period, where the temperature variations have been mostly of the order of 1 degree, and yet civilizations have been seriously affected. So we'll have to think about that as well. And there are within that things like the medieval warming and the Little Ice Age and the Industrial Revolution starting somewhere in the late 1700s and early 1800s, right? So the feedbacks then remain critical in a very simple sense. There is some initial climate perturbation, there is a response, and if the response amplifies the original perturbation, then we call it a positive feedback. We will see some examples of those. And if the initial perturbation is damped and the response reduces the original perturbation, then we call it a negative feedback. So it's like a thermostat for a refrigerator or for an air conditioner, where if the temperature goes up, the air conditioner kicks in and cools it, and if the temperature cools too much, the air conditioning goes off and the temperatures go back up. So negative feedback loops tend to be stabilizing, whereas positive feedback loops tend to be amplifying. So Venus and Mars have had positive feedbacks, which brought them to these very warm and very cold temperatures, for example. Okay, that's the idea. Sun's energy comes in from gamma rays and X-rays at very short, very energetic wavelengths, and by the time it reaches Earth, most of the ultraviolet is absorbed by ozone or is used for producing ozone. What reaches the Earth is in the visible band, and outgoing is in the near infrared and infrared band, and the sun's electromagnetic spectrum also has microwaves and radio waves. So it's a nuclear reactor which is producing energies in all wavelengths. What matters to us is what comes to the to Earth. So as we said before, it's the disk projection of the sphere is a circle, and that's what intercepts the energy coming in. So the area is 4 pi r squared. So you get the solar flux of 1362 watts per meter squared coming in. Okay, we have to account for what is reflected back by high albedo surfaces like ice and snow and so on, deserts. Earth's average reflectivity is about 30%, so 0.3. 30% of that would be reflected back. We often look at net that remains. And Earth takes all that energy and emits infrared back from every point on Earth. So the energy going out to space is 4 pi r squared. So that has to match the incoming radiation. We have already talked about this in our earlier chapters. So we have also looked at these numbers. If we think about 100% of the shortwave coming in, 30% goes out because of the albedo reflected from cloud tops and surfaces and so on. 23% is absorbed in the atmosphere, so 47% reaches the surface, which is bounced back and forth to create energies greater than 109%. Why? Because it's like putting on a blanket and trapping the body heat and creating warmer temperatures. So even though you're only getting 47% here, the heated surface, evaporation, cloud formation, condensation, heating, and so on produce long wave energy that is reflected back to the surface and back to space and so on. So some directly goes out to space, some gets absorbed in the atmosphere, but net you have to have 70% going out as long wave, because it should match 70% of the short wave that is being taken in. The balance on some long time scale, right? Fairly straightforward. So if we take the albedo and the long wave and the short wave coming in, long wave going out, you end up with surplus energy in some latitudes and deficit energy at polar latitudes. As we said, this energy has to be moved to polar latitudes to keep equilibrium. So the equator to pole temperature gradient then becomes very important, as we will see, especially because even with global warming, we are basically perturbing the equator to pole temperature gradient, which means we are perturbing the amount of energy that needs to be transported, and that's what changes the weather and climate and so on. That's what we have to figure out. How does it change?